Tamam, geldi mi tren? Okay, so we are talking talking about scheduling algorithms, and we said that three for all the three scheduling algorithms. Okay, fairness, our policy, and the balance are the main things that we need to be careful about. I am saving, and that's fine, good, okay. Let me turn this on. Okay, so three things, but depending on the operating system type, depending on our computer, some of them are more important than the others, and there might be other criteria to optimize. For example, for the batch systems, the CPU utilization or the system balance is the most important. We don't care about the interactivity. We don't care much about the power usage and etc. So that's to be said. For the interactive systems, it is the responsiveness, user psychology. So we need to know about some human psychology. And for real-time systems, it is the deadlines, okay? Meet the deadlines. I have to give you an answer under some predetermined time. And we talked about those, and we talked about some batch schedulers. I mean, for the batch schedule, we don't have much to do because, I mean, there is no interactivity, there is no optimization of psychological human stuff, etc. So first come, first served, or the shortest first, or the shortest remaining time first are the main algorithms that we use for the scheduling. And of course, for the shortest remaining time first, we need the timer interrupts. We talked about those, and then we started talking about interactive or time share systems. These are the some of the scheduling algorithms that we have discussed yesterday. We talked about round robin, and we said that round robin is very simple. It's like first come first served kind of corresponding thing to the interactive systems, but sometimes it might have some problems. For example, with the round robin, you can't really differentiate between. Where is I drew a nice, maybe not so nice picture yesterday. Where is my picture? Okay, maybe go to the beginning of the. No, I think I should find it. Yeah, this nice picture I'm talking about. Well, you might say that I keep drawing nice pictures, but this is the nicest one that I drew yesterday. So this process A and process B. We know that this one is CPU intensive, doing CPU intensive work. Okay, so this is CPU bound and this is IO bound. Okay, this is using, most of the time it is using the CPU. For a little bit of time it is blocked. It needs some IO, etc. This one does just the opposite. If we use standard round robin for this case, okay, the process A will use more system resources, because by the nature of process A, it is designed that way. It uses more CPU, so it won't be fair. Okay, so the round robin scheduling has these kind of problems. So what is our solution? Our solution is, let's introduce the idea of these priorities. Maybe for these kind of processes, we should increase their priorities so that they get to use more CPU time. Okay, if both of them are available, then give your priority to this process B, because I know that the process B will give up the CPU in a very short amount of time anyway. Okay, then process A will start working. That's how you satisfy this criteria of fairness. Okay, criteria of fairness. That's what we said, and then the question is, how are we going to know that one process is an interactive process and the others are not? Well, it is not that easy to know it, but we can always check how much of their allocated time, quantum time, they have used for their last run. If I have given a process 25 milliseconds, and if that process used only 5 milliseconds of it, that means that maybe I should increase the priority of it by 5, okay? Because 5 over 25 is very little time of it, so I would increase its priority by 5. So next time when I make a decision, I will put that process before the other processes that use their times more efficiently. Okay, so that's called dynamic priority adjustment, and for the dynamic priority adjustment, I mean, we don't care with this one. We don't care if the process is interactive or not. We just look at how much of their allocated quantum time they are using. If they're not using the whole quantum time, then we are going to give them priority. Sometimes this might sound a little bit counterintuitive. I mean, I gave you the CPU, you didn't use it, it's your fault. No, it's not their fault. It is, you cannot expect a word processor to use the CPU for the whole quantum time, because it is their nature. I mean, the word processor works that way. They are designed that way. On the other hand, if I have a numerical application that tries to calculate the 1 billionth digit of the number pi, that process doesn't need any input output. I mean, if I give them the CPU, it can use the CPU for 200 years, right? So we shouldn't make it fair to the word processor that it is designed that way. That's why I keep its priority over the others. Okay, but the thing is that if I started changing the priorities one by one for the all processes, and as you know that there might be more than 1,000 processes running on my computer, that's going to be lots of tasks, lots of things to do for the operating system. That will make our scheduling a little bit slow. If the scheduling is slow, the whole computer slows down. Why? Because every time I make a decision, I am running very complicated algorithm and etc. So they have invented these run queues. Okay, so I have priority classes, and from time to time, when I say I am increasing your priority, maybe I am increasing its priority class from priority 2 to priority 3, etc. Okay, and if I see that one process is using too much CPU, maybe I should lower its priority so that the other processes can use the CPU. Okay. Yesterday somebody asked a question, where do we keep all that stuff? I mean, how much CPU I use, how much system resource I am using. Of course, it is in the process table. That's why process table, design of the process table, and the processing of the process table is something important. Kernel keeps using it, especially for the scheduling. At the process table, you have all the things, many things, and I'm going to show you this task manager again to show you what kind of things I keep in my process table. I think I go there and I always forget where I get all the, okay. These are my processes, and these are some of the things that I keep on my processes. For example, this my draw board, I cannot make it larger, I am sorry. Maybe if I do this, I will make it larger, right? Yeah. Take a screenshot. Did I get a screenshot? Oh, I know the problem, because it is over the top of everything. That's why when I say, okay, so I take this screenshot. This is my, okay, now I can make it larger. I couldn't make it. Okay, do it and take the screenshot. Okay, so it looks like my draw board, okay, it is using not much CPU at that time. It is using this much of the memory. It is using this much of the disk bus capabilities, and this is my network, and I think there is a way of expanding this, like how many threads I am running within this process, okay, how many threads I am running, and how many page faults I am causing, how many pages I am keeping in the memory, and etc. So all that information is kept in my process table. When you make a scheduling decision, you make this scheduling decision by looking at the process table. So process table is something very critical and very complicated. And the thing is that I don't want it to be complicated, because if it is complicated, then it will take lots of time to process it. And every time when I do a scheduling decision, I will get that hit as a penalty for my operating system, because scheduling has to be fast, fair, balanced, and policy enforced. Okay, so we talked about those, and varying quanta, we said that maybe along with the priorities, maybe the quantum time is something important. Maybe, I mean, we like longer quantum times, because that will lower my context switch penalty times, okay? Longer quantum times is good, I like it, but longer quantum times are bad for the interactivity. But maybe I can say that for some certain priorities, high priority processes, maybe I can keep the quantum time small. For the low priority processes, I can keep it large. So I am trying to find a balance between context switch time and the interactivity. Okay. So that's another thing. So what did we do? For each process now, I have the priority and the quantum time. And priority and quantum time are kind of tied to each other. Lower the priority, longer the quantum time. Okay, so we talked about these, and yeah, another question is how do I assign my priorities? Okay, so this is what I said. I mean, at the beginning I wouldn't know which processes are interactive processes, which processes are not interactive processes. I mean, you should not trust the application itself. If the application says that I am an interactive process, so keep its priority high, that process might be cheating, right? You don't trust the processes, so you have to kind of figure this out yourself. Unless that process is a system process. In that case, if a system process says that I am the kernel process and I am important, if something happens, you have to give me the priority. So some kernel processes, the priorities are high. For interactive services, for example, in my kernel, well, in Unix I don't do this, but in Windows, the interactive services such as the handling of the windows is done by the kernel. So if I am handling something about windowing, moving the windows, resizing the windows, and etc., then maybe that process should have a higher priority, etc. And if there are some nice users, okay, user says that, well, this process is not that urgent, so you may keep its priority low, okay? Well, in that case, maybe I should use that information too. A process voluntarily says that my priority is not high, it is low, so I should lower its priority maybe. Maybe I shouldn't trust the processes that says that I am important, because that might cause some problem. But if a user says that I like to lower my priority, then take it. Remember what was the name of the utility that lowers my priority in Unix? Nice, yeah. Okay, so it is important to be nice all the time. So you just nice it. You said that I am going to run this nice, for example, my application. You just give the application like a command line parameter to this nice command, and it runs this application in a lower priority. So nice app. Okay. So we talked about those, and the Unix priorities. In Unix, usually, okay, lower numbers indicate higher priorities. That's how they designed it, okay. And priority 1 means that it is the highest priority. So if you nice a process, okay, if you add 20 to it, so you are lowering its priority, okay. And niceness can be negative. Negative nice means that I am not nice, but regular users cannot use negative priority values. Okay, I don't know where I got this. I think I got it from the book, maybe. I think I got it from the book. So these are the priorities. Lower ones, for example, 75 is the highest priority one. This one is the lowest priority. And the last one is the already running one. Okay, so. Well, I mean, for Windows, priorities are different. For Windows, Linux, and Unix, it is different. But usually the modern operating system, they support this idea of priorities. Okay, because they are some nice way of satisfying this fairness among the processes. Okay, so let's remember our batch scheduling algorithm, shortest remaining time first. Remember the first come first served approach? We said that in the batch systems, okay, first come first served kind of works, but if I know their running times, maybe I should run the shortest process or the shortest job first so that my throughput will be optimal. Why don't we use the same idea for the interactive processes? Can't we do that for the interactive processes? The answer is, well, it is not that easy, because for the interactive processes, I really don't know how long they are going to take. Okay, I really don't know how long they are going to take, and since, I mean, they will be switched back and forth between these processes. I mean, for the given quantum time, I don't know if that process is going to use the whole quantum time or that just a little bit of that quantum time, right? So it changes from time to time. What are we going to do then? Okay, so we are going to try to guess it. Okay, how are we going to do that? We know, as the operating system, I know that the last time I gave the CPU to that process, it used, for example, 20 milliseconds of CPU time. Previously, it used 15. Maybe I can take a weighted average of these two times to make a decision on how long it's going to use the CPU for this time. It's just a very, very, very approximate guess. There are no guarantees that it's going to use that time. So that's what's going to do. T0 is my process used my CPU T0 seconds. T1 is, okay, this is previously, I remember, okay, T0 at the beginning it used this much of CPU for when I give the CPU, and then it used this much. For T2, okay, for T2 I don't know how long it's going to use. I am going to run this formula. I am going to choose an alpha, for example 0.5. Alpha should be between 0 and 1. Okay, if alpha is 0.5, that means that just 0.5 times T0, 0.5 times T1. Okay, so that will be just the average of T0 and T1. So T2 maybe should be average of T0 and T1. That's my guess. So maybe I can make my decision based on this guess. If it is long, then lower its priority. If it is short, make its priority high. Okay, so I have three numbers. After the process runs, I have three numbers, and keep running this formula. Remember, this becomes my T2 now. Okay, and I can multiply this T2 by alpha again, and it turns out that my the T3 is going to be this way. So it's called taking the running average, okay, running average of the quantum times or the CPU usage times, and every time you get affected from, if these are my real numbers of CPU usage, sorry, the 4, so okay, so using this formula will tell me how long my process is going to use my CPU for the current quantum time, and it will be affected from T0, T1, T2, T3, and T4. But depending on my alpha, if I keep my alpha small, 0.1 for example, if it is 0.1, I will get affected from T0 very, very little. Mostly I will get affected from T1, from the close by ones. Okay? So that's kind of an adaptation of the shortest remaining time next approach, and it is an approach for the interactive systems. It is not, of course, exactly the same. The main problem is I don't know how long it's going to take for this interactive process to use the CPU. For the batch systems, I have better ideas. Since they are not interactive, since I know what they are going to do, it will be a much solid number for me to know how long it's going to take. Okay, so that's the shortest process next. Once I know it, I can change the quantum times or the priorities maybe. Yes?
But at the beginning, it's totally random, right? The priorities.
At the beginning, their priorities are all the same.
Oh, so.
Yeah, because if I don't know it, they are all the same.
So the selection is random. Selection of the process.
It's sorted. Selection is first come first served, round robin, right?
Oh, okay.
We are all talking about round robin, right? Yeah. I mean, maybe I am running a few round robin algorithms depending on the priority queues, maybe a one. Okay. So the thing is that round robin I am running it, but round robin needs a quantum time, and within the same priority queue I can change the quantum times.
So does the interruption does it affect the quanta values of the processes? I mean, when the process is started, after
a process is running, interrupt happened.
Yes, happens. And it's
operating system handled it.
Yes.
And operating system says that this process is still running and it has more time in its quanta. Okay. So let's go back to that process now.
So it makes it greater quantas, right?
No. Well, no. The important. Well, you are saying that. Do I consider the interrupt handling time?
Yes.
As the I mean, where should I bill it? Okay, if you think it like a billing approach, okay, who should I charge the CPU time of the interrupt handling? Of course, it is the operating system's time. Operating system has processes too. They are processes, right? So you should charge that time to the operating system so that I know how much time the operating system is using. If the operating system is using 30% of the CPU time of the whole computer, then I am doing something wrong. It's like a government. Government says that, okay, this whole country, we are producing $10 billion, okay? But out of that $10 billion, we are spending $3 billion for the government work, for the schools and for the judiciary and security and the army and etc. Is 30% high, very high for the government budget? Well, kind of okay, but if it is 80%, then that's definitely high. Okay? So, definitely no. Don't charge those process handling times or interrupt handling times to the processes. Processes have nothing to do with them. Okay? Sometimes, I mean, this doesn't happen with the context switching, but it happens a lot with the memory problems. I mean, if you are out of memory, you will keep loading your process data from the disk all the time when the context switch happens. Okay? In that case, sometimes your operating system is busy 95% of the time loading the data from the disk and writing the data to the disk because I don't have enough space. When I do a context switch between two processes, if my data is not on the memory, then I need to load everything from the disk, right? and I am in 50 milliseconds, I am going to just do the opposite. Again, I am loading everything from the disk again. So I am spending 95% of my time loading data from the disk and writing data to the disk. That's called trashing, and trashing is the worst thing. Okay, that can happen to the operating system. Operating system is alive, but it cannot do anything useful because it is busy doing these kind of operating system services. And we will talk about that. Keep your operating system simple, but simple doesn't mean that it is unfair. Simple doesn't mean that it doesn't provide protection. Simple doesn't mean that it doesn't abstract the hardware away, the details of the hardware away. So that's why operating system design takes some careful thinking. Okay, another scheduling algorithm is this. Forget about the processes. Okay, if I have a CPU, if I have n users, or maybe for each user there is a process, I am going to give you 1 over n of the CPU time for each user. And I'm going to measure the actual CPU usage. And depending on the CPU usage, I am going to change the process's priority depending on how much it is using. So it's called guaranteed scheduling. Okay, guaranteed scheduling. It's like what the government does to guarantee that I don't have enough number of females working for the government, so I am going to allocate these job slots for the women. Okay, I am going to say that for the next 100 person I am hiring, 80 of them will be from the women population, something like that. Okay, so that's kind of guaranteed scheduling. You guarantee that each process, whether it's an interactive or not interactive, will get to use 1 over n of the CPU time. Okay, guaranteed scheduling. Another scheduling is very nice idea. How about these priorities? I mean, remember the problem with the priority inversion? Let's go to this picture again. If I keep running pure priority scheduling on this picture, the problem is this. One is the starvation, right? Starvation. If these three processes are busy, they are doing something, they are always ready to run, their priority is high, I keep running this over and over and over again. So these tasks or this task will not have any opportunity to use the CPU. That's one of the problems, right? That's the problem. Starvation is the first problem. The second problem is the priority inversion. This one holds the lock. This one needs it. Okay, this one holds the lock. This one needs it. But this one is blocked. Since this one is blocked, this one and this one is taking the CPU all the time. Since these two are using the CPU all the time, this one is blocked, right? And this one, it doesn't get to use the CPU. So, in an effect, this process is waiting for other processes to finish their job so that this one get the CPU. The worst thing is, maybe this one is blocked too, and this one is blocked too. They are all blocked, but these one all running in the run queue. Maybe these three are waiting for the lower priority job to finish it, but it cannot finish. So these three are in effect waiting for this priority Q3. So that's the inversion of the priority, right? Priority inversion problem. So we need to have what was our solution? We could say that if a process is not running for a long time, maybe I should increase its priority. If a process is running too much of the CPU time, maybe it's lower the priority. Or I can do this nice approach of lottery scheduling. Piyango, lottery is piyango, Turkish, okay? So give each process lottery tickets, piyango bileti. So each process is given some lottery tickets, but higher priority processes get more tickets. Let's say priority Q3, 2, and 1. I have 2 processes here, 3 processes here, and 1 process there. I am going to give 1, 2, 3 tickets for this one. Okay, ticket number 1, 2, 3 is here, 4, 5, 6 is here. For this one I am going to give 7 and 8, just 2 tickets, 9 and 10, 11 and 12, and this one will get 13. So there are a total of 13 tickets. So now I am drawing a number, a random number from 1 to 13. Let's say it's a uniform distribution. Let's say I picked 7. 7 is here. Okay, so P2 gets to run. Okay, this process gets to run. Even though it has a lower priority than these 2, it gets to run. But the thing is that these 2 processes have a better chance of running, right? Because they have more tickets. If I like to increase their chances even more, give them 50 tickets. 50 tickets, 2 tickets and 1, 2 tickets and 1 ticket there, right? So this way, starvation will not happen. Okay, starvation will not happen because everybody has a chance to win the lottery. Well, P1 has the smallest chance of winning it, but it has the chance of winning the lottery. And higher the priority number, better their chances of getting the CPU time. So getting the CPU time is like winning the lottery. Depending on how many tickets you have, you will have a better chances of getting the tickets. Okay, so that's the idea. It's not pure priority scheduling, but it kind of serves the purpose, right? Serves the purpose. Okay, so give each process lottery tickets. Higher priority processes get more tickets. At scheduling time, pick a random ticket from 0 to whatever. It's like the milli piyango çekilişi gibi. Then the process holding that ticket gets to run. Okay. The nice thing is that this, if I am trying to get a lock, that lock is taken by this process P1. Okay. I can give temporarily my tickets to this process P1. So you may transfer your tickets temporarily to some other process so that process runs and releases the CPU. That's what we say. Tickets can be exchanged between the processes, such as the client and server, or a process that holds the lock. Okay, so that's the idea of lottery scheduling. Scheduling is something important, something critical. That's why we have lots of algorithms. And you will never see in Windows, you will never see that I am using this scheduling algorithm or this or that. They usually use a hybrid version of it, but at the bottom of it, you will see a round-robin scheduling. Okay, it's in turn, right? Now you run, now you run, now you run, etc. And priorities and round-robin are the 2 main things. Another scheduling approach is fair share scheduling. Okay, you say that I don't care about the process, I care about the users. I have a mainframe computer, 50 users are using the mainframe, and if I try to be fair between the processes, okay, I have 50 people using the computer. Each one has some processes, person 1, or maybe I should say user 1. And user 2 up to user 50. Okay, so they are using it. If I try to be fair between the processes, that might give me some trouble. Why? Let's say this user number 2 is forking from P2 1 to P2 100. Okay, this user forked 100 processes, and all the others P11 and P150. Okay, all the others have just 1 process. That means that this guy is going to take more than half of the CPU, right? user number 2. I don't like it. So the solution is make decision based on the CPU consumption of process. Okay, so between the users, tell okay for user number 2 it is using half of the CPU time. In fact, it should use 1/5 of the CPU time. Okay, so that's what we are going to do. We don't want to encourage forking just to get a larger share of the CPU. The solution is try to be fair between the users, not between the processes. So if I keep forking lots of processes, their priorities will get lower and lower. Okay, that's called fair share scheduling. Any questions? I think I'm done with interactive scheduling algorithms, and well, I mean you can increase the the number a lot. Your imagination is the main tool, right? Yeah, just make up new new scheduling algorithms yourself. They did. I just give you some ideas, but all the time we kept talking about this round robin algorithm and the priorities. So all of them are kind of variations. How am I going to use this round robin algorithm? With the round robin algorithm, we have the quantum time. How can I play with the quantum time? And how can I play with the priority numbers? Okay, so this one changes the quantum time by looking at the estimated running time. This one says that, well, nobody is going to be starving. This one says that, okay, I'm going to use this new creative idea of lottery scheduling, so I am going to prevent this priority inversion, and this one is about how about the user, etc. Everybody has a different motivation. Okay, any questions? So the motivation is definitely very different from the batch systems. It is all interactivity, staying interactive. Staying interactive means that priorities and the quantum time. Okay, if there are no questions, let's move to the last class of scheduling algorithms. It is the real-time systems. As we talked about it before, real-time systems are all about meeting the deadlines. Okay, I need to be predictable. I can't be satisfied by the answer of I don't know how long it's going to take for you to take the CPU. It might take a while or it might be immediate. I don't like this answer, no. I need to know that if I need the CPU, I need to have a guarantee that I will have the CPU in 50 milliseconds, 100 milliseconds. Otherwise, I am trying to control a nuclear power plant. Okay, otherwise things will get nasty. Okay, I am trying to control the braking mechanism of a car. If I don't get the CPU in 10 milliseconds, this car might crash. Okay, so those are the time critical jobs, and real-time systems are good for those kind of specialist cases. So they need their own scheduling algorithms, and the most basic scheduling algorithm for the real-time systems is this. As I said before, for the real-time systems, remember we didn't have the protection hardware for the real-time systems. Do you remember why? We don't have protection. We don't have memory protection. Do you know why we don't have memory protection? Why we don't have to have? Maybe I should ask it that way. We don't have to have memory protection between the processes for the real-time systems because that would make a nice midterm exam question, actually. What is the protection? What's the protection hardware? The protection hardware is the mechanism that prevents one process to access the other processes memory, right? So when I try to access the other process's memory, the hardware stops me either, or there is no way to access it. Okay, but for the real-time systems, I don't need such protection, just to keep these things cheaper. Why I don't need protection between the processes for the real-time systems? Yes?
Usually, real-time systems are restricted, so you don't have to just load another process. Yes.
They are specialized operating systems, right?
Yes.
And their processes are specialized. They are not general purpose computers. They are not general purpose operating systems. The processes are already on the operating system, and as the end user, you are not allowed to add new processes to this computer. Okay? I don't know, and I can't add a new process to my computer that controls my braking system on my car. Okay? I can't run an ordinary process on it. So I know that on this computer there are three processes. Okay? One process, P1, controls the braking mechanism of my car. P2, let's say, controls the thermal values of the car. For example, my engine should not be too hot or too cold, etc. And the process number 3, for example, it controls the wheel spin. Okay, maybe I shouldn't spin my wheels too much. That will be bad for the car control, and that will be bad for the stability. Okay, so each one needs 100 milliseconds of the CPU time every 300 milliseconds. And the operating system says that, okay, I will give you 100 milliseconds, okay, and nothing more, nothing less. You will get this one, and after you are done in 100 milliseconds, you will get the CPU in 200 milliseconds, okay. So that's how you are going to run, and this process knows it, and this process knows it, and this process knows it. There is no way that I can add any other process on this one. This is not a general purpose computer. This is not a general purpose computer. That's why I don't need protection between these three. P1 is carefully written, P2 is carefully written, and P3 is carefully written. They don't try to reach each other's memory positions. Okay, they kind of cooperate to manage the whole car. Okay, so that's one example for the real-time systems. And well, this is a very simple case. You might say that couldn't this be like 50 and this is 75? Yeah, it could be. This is how you design your scheduling algorithm for this real-time system. Okay. So they usually work this way, kind of round robin, right? It's a kind of round robin. There is nothing much to make a decision of. P1 runs, then P2 and P3. And I know their starting times and ending times. And if P1 doesn't use this whole 100 milliseconds, then I wait until P2 gets this 50 milliseconds. So some of the CPU time is wasted. And here, some of it wasted, and here, some of it wasted. And in fact, for the most real-time systems, you design your system in a way that your load factor is not greater than maybe 60%. So you intentionally keep 40% of your CPU time idle, in case something happens and I need that CPU time, because this is time critical stuff, right? Okay. And some people do this. Some people say that, okay, idle process, IP, and it will take 25 milliseconds at the end of the whole cycle. So it is empty. If something happens, I am going to use that part. Okay. So real-time systems that work that way, the ones that I'm talking about are the hard real-time systems. The meaning is there are absolute deadlines that must be met, or else you are junk, okay? Or else you are not useful for me. Those are the hard real-time systems, and these kind of systems are common, but more common ones are the soft real-time systems. They say that I will make every effort to meet the deadlines, and 99% of the time I will give you those deadlines. Yeah, that's fine. But 1% of the time I am going to miss some of the deadlines. Okay? Soft real-time systems. Obviously, I cannot use the soft real-time system to control my car's braking system, right? That would be too dangerous. I mean, I cannot trust my life to some machine that says that there is a 1% chance that you are going to die today. No, I am not going to do that, right? So that's not a good thing. But let's say, for example, the multimedia systems, I have a screen, I have a machine like this, okay? I am showing video. Showing video means that I need to show 20 frames per second. Okay? FPS. 25 frames per second, I need to show it to the user. So that's time critical. But what happens from time to time? Every hour, for some of the seconds, I show them 23 frames. Most of the people will not realize that I showed them 2 frames less than the original. Some people may realize it, but what would you do? I mean, would you throw this away? No, you would say that it can happen from time to time. So there is just a small flicker, right? We can tolerate it as human beings. But if it is happening every other second, sometimes I am showing 26 and sometimes I am showing 20, I am not going to watch that movie. Okay? So free time system says that most of the time I am going to show you 25 frames, but sometimes from time to time, 5% of the time, 1% of the time, I might show 24, okay? Or 20 or some other number. Okay, those are called soft real-time systems, and soft real-time systems are usually based on Linux, okay? Because Linux is not designed as a real-time system, but it can be used as a soft real-time system. Okay, any questions so far? Okay, if there are no questions, okay, silence is not a good thing for me, because if a class is silent, that means that they are not going to do very good in the midterm or the final exam. If they are not doing very good in the final exam and midterm, that means that next year this class will be more crowded. That next year there will be more silence then. Okay, so think of some questions, and after 10-15 minutes of break we will be continuing. It is 11:35. Open the windows please. Where is my attendance? Başkasının yerine imza atan oldu mu arkadaşlar? Değil mi bakıyor? Ne zaman geldi?
Hayır, formüllerini anlamadım. İnternetten baktım. İkinci, üçüncü var ya. Var. Bunda ne yapsam? Ben şu an bilgi hesapladım ya, bana şöyle değerler verdi. Bundan ortalaması yanlış. Ya bana şöyle bir değer gelmiş. Aynen. Sadece bir tane.
Sonra ne yapacaksın biliyor musun? Vardı istediği şey şuradaki tüm x'ler üzerinde loop yapman gerekiyor. Şöyle bir loop yazayım. Ve all yapacağım. Burada şunu yapman gerekiyor. Mesela xi diyorum. Xi eksi karesi, bunu da şey alıyorsun, bir tane toplamın olsun. Sürekli şunu alıp karesini alıp konuşuyorsun. Alıyorsun, karesini alıyorsun. En son tüm x'ler için bunu yaptığın zaman toplam eşittir. Toplam bölü n eksi 1. Yani x şu mesela 1 için 1 eksi mi yapıyorsun, min x. Bunun karesini alıyorsun. Toplamı 6 için yapıyorsun. Sonra 4 için, sonra 7 için, sonra 10 için. Bittikten sonra da n eksi 1. Yani kaç tane?
Yine bana eksi bir değer gelmiş. Şey için,
Aynen. Yani var istediği şey yine böyle bir yetmiş gibi bir şey yani. En sonunda şu mesela var dediği şey de o da nasıl hatırlayayım, şurada yazmıştım. Mesela onu şurada şey yapayım. Burada da diyelim kovarı nasıl aldığına bağlı. Mesela x, y diyebilirsin, y, z diyebilirsin. Orada bir tane şey var. Çıktı matrisi görmüşsünüz belki, tam hatırlamıyorum. Normal çıktığında şöyle bir şey olması lazım. Var x, işte kovar, x, y falan filan. Yine burada da diyelim hani var diye kovar bir şey var. Çıktıda bu matrisi bulabilmek için bunları hesaplıyoruz aslında.
Bu zaten var.
Aynen. Şimdi nasıl kovaryans bulabiliriz? Bunu da şöyle bir mantık var. Yine şöyle bir x'i yapayım ben. Burada aynı anda yine bir tane loop'um olacak. Loop at all x and y diyorum. Bir tane şey tutsan yetiyor zaten. Yani bunun x'in biri y'nin biri olarak yapacağız çünkü. Ben loop dedim. Burada şöyle i eksi yine mini çarpı y i eksi mini.
Çünkü mesela ben de
yine bunu toplamam.
Y'yi almıyor
Z burada yok yani şöyledir. Kovaryans dediği şey sadece iki değerli için hani y, z gelir. Şu matrisi tam hatırlamıyorum.
Ha, burada işte tam şey var, anladım. Mesela x'ye x'ye de olur.
Aynen. Onlar var böyle. Burada 3 satır mı ne olması lazım. Hani yerleri değişebiliyor. Ona göre end loop diyorsun. Yine toplamı bölüyorsun.
Burada kullandığım x'ye y ne şurası mı?
Aynı form.
O zaman şey kullanıyor mesela böyle. Burada hesapladığım şey. Ama olmaz ki o mantıklı şey gibi. Burada tezgah var oluşuyor ya.
O problem değil. Yok o problem değil. Mesela kovar dediğin zaman bunun sonunda da yine 80 gibi bir şey oluyor. Ben en sonunda ne yapacağım? Min x'ten var x'ten 70 geldi. Kovardan 80 geldi. Bundan 110 geldi. Falan filan yine böyle bir matris oluşacak. 90 oluşturuyorum. Sonra bunu gideceğim dosyaya yazacağım. Sonra ana gazet gelecek bu matrisleri toplayacak, bu matrisleri bir işlem yapıyorsun orada. Aynen, orada bir diskret hesaplayacak, en yakınlarını bulacak.
Ondan sonra burada bir üçlü oluşuyor. Burada neyin varlığı olur.
Evet yani şu matrisin içinde kullanacağımız her şey mini var veya mini şunun içinde kullanacağız var veya kovar. Onları hesaplayarak bu matristeki değerleri bulmam lazım.
Şunu anlamadım. Burada hesaplarken
Belki
Nasıl ki? Yine sadece bu değerlerle net çıkacak. Yoksa
Sadece bu değerler ve mimler.
tabii şeyi kullanmayacak.
Varı kullanmak. Yok hiç varı burada alakası.
Sonra için kullanırken kullanacak. Hani dosyası
Aynen dosyayı yazarken bunu kullanacağız.
dosyayı şey mi bastırdım ama projesten aldım. Bunu bir format tutmuş mesela. İşte dosyayı yaratıyoruz.
Yaz
Sonra
olmadan
şey
yazılır.
şu,
Yaz olmadan yazılır.
Bunu ana dosya, ana prosesler
Evet, böyle.
Şimdi bakın değerlilikler göndermek gerek var mı?
Orada direkt yazacak
Oraya
yani.
renk görecek. Acaba da şimdi ondan mı çocuğa yazacağız? Gerek yok.
Dese yeter yani. Aynı zamanda bir şey yazmamız.
Küçük proses kullanılıyor ama kullanılıyor. Zaten o şey yazıyor. O formatta yazıyor.
Yani tamamen
Şöyle bir şey yapmışım.
istediğimiz formatta yazın demişsin. Hani çünkü önemli olan ama prosesin onu okuyabileceği şekilde yazmak. Bir daha hesaplama yapacak yani tamamen sağda kalabiliyor. En yakın matrisi buldum mu buldu, bulamadım mı? Ben çok bunaldım. Ben sürekli
Ya çok geç anlıyorum.
yani biz de Esra'yla konuştuk hani mantıkları biraz. Ondan iyiyim ama yine de nasıl bir yazar geçtim zorlanıyorum yani yıllar geçti. Bu kadar yok
Ama yani çocukları
İkisini hiç kullanmadım. Yani
Sizlerle mi durduruyorsun? Ama değil.
şu problem durmuyor.
Ha, çocukların gelmesini bekliyor ya.
Ben çocukları çağırıyorum. Program bitmiyor. Orada kaldım. Programı bitireceğim diye düşünüyorum.
İşte orada aslında yazı bitince bitiyor. Şey, çocuklar bitince hasta ve eğitim yazılmış ana prosesi. Çocuklar bitince bitiyor. Oraya giriyoruz.
Yani
Ben
bir
bakıyorum.
prosese giremiyorum yani. Onu uzatmam lazım ama.
Kanka ben de öyle yapıyorum.
Bir buçuk yıl kaldı zaten.
Kanka yok sana. Kankayı da alıp anlamam.
Yarın sabah. Yarın sabah depresyonu koyup.
Ben bir de alıyorum kontrol geçmiş olsun. Bazen gidiyor depresyon.
Hocam şey, bağlantı koptuğunu görmedin mi? Bağlantı koptu.
Niye kimse bağlantı koptu demedi?
Bence açıktı aslında, ben telefona bakmadım.
Bir gün bile çalıştı yeter haftada. Şey değil yani. Bekar tezimiz program sorunlar. Şu an
yavaştan ilerliyor ya.
Tam yarın ses duydum ya geri bağlandı sonra.
ne yazıyor?
Önce hocam ne mi?
Olur mu? Gelsene ya.
Yazacak bir şey yok zaten. CV yapamadım. CV ona da kalmıştı.
Günde kaç tane sayfa
Gerçekten öyle de bakıyorum.
Bayağı
Onları diyorum.
orada bekleme var. Kaçtığınız eğitim var.
Sağlamıyor. Cumartesi falan da yerlere geliyor. Hayır. Plan önünde. Çok da uğraştım.
Kimse başkasının yerine imza atmadı.
Double block
Normal kontrol yapıyorsun. Yana çıkmıyor.
Dosyalarımız kaydettiğine bağlı. Satır satır kaydetsin okur.
Sana derse bak
Onu sürekli veremeyeceğiz. Siz aslında satır satır kaydettin. İlk başta alt prosesler dosyayı kaydedecek ya. Orada kaydederken mesela benim aklımda var.
Ama oradaki prosesler bir şey dosyada
Onu satır satır
kullanacağım
yani.
şeyler.
Zaten mantık
File
kesin
alsın.
şöyle bir şey.
O dosyada
Satır satır satır kaldı.
ben şimdi okuyorum.
Satır satır.
Görüşmem devam ediyor.
Öyle zaten kanka şey yapalım. Ben hep yapıyorum.
Yardımlaşayım mı?
Bakayım. Ben daha şey değil.
Ablanın yerine.
Yok Allah aşkına de ama arkadaşlarım var. Şu an erken geldi. Hayır tam vaktine geldi.
Kullanılmıştır yani.
Okay, so hard real-time systems and soft real-time systems. Again, there is not much an issue in terms of making a scheduling decision in real-time systems. Everybody has their own slot, and everybody has knows how much time it's going to use. The one of the classical problems with the real-time system is that how many processes can I load up to the system, and can I still keep?
Hocam dersten düşmüş sanırım ama öyle dediler gruptan kontrol edebilir miyiz?
Okay. How many people are there? Just one? Just me? Two. Good.
Hocam geçen dersin biraz ortalarında düşmüş sanırım.
Okay. So the thing is that how many processes can I load to this system without breaking these rules, hard time rule? So this is called schedulability. Okay, can I schedule this many processes? Okay, so this rule has to be satisfied. Okay, many real-time events occur with a regular frequency. It says that I need to check the brake pads temperatures every 20 times a second. I need to check the engine temperatures 2 times a second. I need to do this and this and this. There are, let's say, total of M processes. Okay, I have M processes, total of them, and process I needs CI seconds, and it occurs every PI seconds. Okay, so let's say one of the processes says that every 2000 milliseconds I will run, and I will take 200 milliseconds of CPU time. Okay, so that's what the processes say. So if I keep collecting these numbers like this, and if I add them up, of course it should be less than 1.0, right? It should be 1.0. If this number is greater than 1.0, okay, then that means that I cannot handle this many processes with these kind of needs on my real-time system. Okay. If this number is greater than 1, then it means that this real-time system is not realistic. It is not schedulable. Okay, so let's give an example. Schedulable real-time system. Let's say I have 3 processes. Okay, with 3 periodic events, the periods are 100, 200, and 500 milliseconds respectively, and these processes, when they run, they use 50, 30, and 100 milliseconds of CPU time whenever they occur. So it's going to be 100 over, no, it's going to be 50 over 100 plus 30 over 200 plus 500 over 100 over 500. Okay, if you add them up, you will see that it's going to be 85, 0.85, which is less than 1.0. So it is schedulable. Okay, and in fact you don't want to be very close to 1.0 in case some of the processes took longer and something happened, etc. So what I am trying to say is that scheduling algorithm for the real-time systems are simple round robin. Okay, there are no priorities. There are no quantum times that you can adjust. The process says that I need to check the temperature of the brakes every 200 milliseconds, and you can't do anything about it. And it says that I need 30 milliseconds of CPU time, and that's it. Okay, so the process already knows how much time it needs, and process has its needs. You cannot, as an operating system, as a scheduler, you cannot change these decisions. Okay, that is against the design principles of the real-time computer. So what am I designing here? I am not designing much, but what I'm saying is that if I'm designing a real-time system, then I cannot run more than 3 processes with these needs on this real-time computer. Yes?
The time between the required CPU time and the period is context switch time?
No. Well, I mean, see, this one says that, okay, I am going to run every 100 milliseconds, and I am going to use 50 milliseconds of the CPU time. If this is my CPU, that means that this process is going to get the 50% of my CPU time. The rest of that time, 50% of the time, will belong to other processes. Okay?
Well, the second process starts in 200 milliseconds.
It says that every 200 milliseconds I am going to run, and I will take 30 milliseconds. So every 200 milliseconds I am going to run, and I will take 30 milliseconds. That's what it says. So it doesn't need more than 15% of the CPU time. And the last one is say that every 500 milliseconds I will run, when I'm going to use 20% of the CPU time. Okay, so if you add them together, that will be my schedulability. Well, you might say that, well, I mean, what is the smallest common multiplier of these 30, 50, and 100? I mean, it might be a very large number. That's why it's a soft real-time system. I mean, if this one happens every 100 milliseconds, all right? I mean, this one says that every 100 milliseconds I am going to run. Okay, so that means that so this is 100 milliseconds. Every 100 milliseconds I am going to take 50 milliseconds of the CPU time. This guy says that every 500 milliseconds I am going to run, I am going to take the 100 milliseconds of CPU time, right? So in a hard real-time system, these two cannot be satisfied at the same time, because this guy says that every 100 milliseconds I need to run, and I'm going to take 50 milliseconds, and so it just only leaves 50 milliseconds for the other people, other processes. I cannot fit 100 milliseconds inside this 50 milliseconds, right? So that's why it is a soft real-time system. From time to time, I will be a little bit late, but in overall, I can say that, remember my example, 25 frames per second. If you take the average of the frames per second for the whole minute, it will be 25, but for some of the seconds it will be 24. For some of the seconds it will be 26. Okay. So these are the periodic events for the schedulability. Again, for the hard real-time systems, the things are already there. Okay. So the aperiodic events, I mean, you might say that not all processes are periodic like this. From time to time, I need to handle events that happens aperiodically. For example, somebody is pressing the brake pedal. It doesn't happen often, but when it happens, I need to handle it. For that, I need to use some time. Well, the idea is the same. The total load must be less than the total capacity. That's what we are going to say. And for some for example, the computers for the spacecrafts, right? Those satellites, communication satellites, those spy satellites, observation satellites, etc. They are all real-time systems, okay? And they are designed in a way that their load is not more than 50% in case something happens. Even the rarest process taking the CPU time, it has its own allocated slot in the CPU time. Maybe most of the time that time is not used, but it is allocated. Okay, so the number one goal for the space satellite computer operating system is the job is affected, the task at hand. Whatever happens, you will keep running. Okay, I don't care about the CPU utilization. I don't care about the battery management and etc. Whatever happens, you will keep running. Okay, and you are going to run every second 20 times, and I'm going to make it possible. I'm going to give you CPU. I mean, those kind of systems, I mean, usually they send 3 computers, copies of each other. 2 of them are running exactly the same thing. They always keep running. Okay, this is a hot backup. One of them is running, the second one is running exactly the same thing, and third one is a cold backup. It is waiting if something happens to the other 2, because once it is launched, you can't fix them. You cannot bring it back, and you can't fix and send it back. Okay, so at the end of this chapter, we talk about thread scheduling. I mean, we always talk about process scheduling, and we said that whatever we are saying is valid for the thread scheduling too. But depending on how you implemented your thread library, I mean, if it is a kernel level library, if it's a user level library, your scheduling algorithms might change a little bit. Remember, let's say if I have implemented my threads in the user space, kernel doesn't know anything about kernel doesn't know what's happening inside the process. Kernel thinks that there is only one thread available for this process and for this process, but in fact there are 3 threads happening here and 4 threads happening there. Okay, so this process is responsible for scheduling between these 3 threads, and this is 4. So this is one possible scenario in this case. So in this one, the kernel says that, okay, process A will take the CPU and it will use it. Inside this process A, the thread scheduler says that you will run this A1, A2, A3, A1, A2, and A3, and these are the A1, A2, and A3. Okay, and this continues until the quantum time for this process A is over. And these are B1, B2, B3, and B4, the threads of the process B. This is not possible with this kind of environment. You cannot, because, I mean, switching happens. This one switches between the threads of process A. This one switches between the threads of process B, and the kernel switches between process A and process B. It is very difficult to see this kind of a scheduling decision. A1, B1, A2, B2, A3, B3. Because, I mean, switching from A1 to B1 requires for the kernel to switch from process A to process B, right? Well, you might say that it's a good thing. Why? Because if I keep switching between the threads of A, okay, that's a less context switch time than switching from A1 to B1. Because when you switch from A1 to B1, you are changing your address space. Okay, everything changes. Much more expensive switch than switching from A1 to A2, right? So maybe it's a good thing, you might say, right? It's a good thing, but the problems with this kind of approach. If A1 blocks, rest of them will block. That's not a good thing. And the kernel that, well, if I have a multiple CPUs on my computer, I cannot run A1 on the CPU 1, CPU 2, and CPU 3, right? That will be a problem. That will be a problem. We already know about those. If the kernel knows about the threads, then this will be possible to A1, B1, A2, B2, A3, B3. Why? Because kernel knows that there are 3 threads there, there are 4 threads there, and I can switch between those. Okay? So you might say again, this is not a good thing, but the kernel knows that this is not a good thing. Okay? Kernel knows it. Kernel knows that it is better to switch from A1 to A2 than switching from A1 to B1. So maybe the kernel is smart enough to use that idea. It will maybe favor switching between the threads of the same process. Or it will say that why don't the threads of this process be on CPU number 2 and press the threads of CPU thread A on CPU number 1. That way the context switch time will not be that big problem. Okay, so the thread switching and process switching are not that different depending on where you implement your thread libraries. The thing is that if you are doing your scheduling yourself, thread scheduling yourself, you can get creative and take advantage of this picture, such as this one. Remember our client server architecture that uses the thread, worker threads and the dispatcher thread. Do you guys remember that one? Dispatcher thread. There was this is my process, a server process. Inside this process there was a dispatcher process, this thread, and there were these worker threads, right? So whenever I get a new request, this dispatcher thread assigns this request to one of these worker threads. Okay, so one of the worker threads start working, and it will handle it, and this dispatcher threads keep dispatching the received jobs. Okay, suppose I am doing my scheduling decisions inside this process, so user level thread scheduling. My thread scheduler saw that, okay, the dispatcher said that handle this. Okay, worker 1 is working on that process, on that job, okay, and worker 1 is blocked. Okay, when the worker 1 is blocked, should I schedule another worker or should I schedule a dispatcher? Okay, I know that dispatcher is the special one. It kind of organizes all the workers. So my scheduler makes a decision, say that no, every time a worker thread is blocked, I will let this dispatcher thread take the CPU and make a new decision, or take the new request and handle it. So I can make these kind of customized scheduling decisions if I am implementing my processes at the user space, not at the kernel space. Because if I handle it in the kernel space, the kernel doesn't know the difference between a dispatcher thread and the worker threads. Okay, so customized scheduling decisions are possible with user level threads, and we talked about this previously. And I think the example that we gave you is the Java virtual machine garbage collector thread. For the Java virtual machine garbage collector is important, and it has to run from time to time. maybe I should consider that garbage collector thread a special thread and give it more opportunity to use the CPU. Okay. So that's all that's all I like to say about the thread scheduling. Any questions about thread scheduling? Not much different from the process scheduling. Maybe the few things that we need to remember: switching between the threads is cheaper than switching between the processes, and maybe we can take advantage of it while scheduling threads. And also the user level implementation and kernel level implementation, they have there again, in terms of scheduling, their own advantages and disadvantages. Good. Okay, if there are no questions, then I will, at the end of this chapter, there are two classical problems that everybody knows: the dining philosopher's problem and the readers and writers problem. I am going to spend my remaining 20 minutes on these two problems. Okay, so the dining philosopher's problem has nothing to do with the philosophy. It has nothing to do with eating pasta. Okay, it has nothing to do with the hygiene and etc. P means process. Okay, so I have here process number 1, process number 2, process number 3, process number 4, and process number 5. 5 processes. They are running on a single CPU. I need to schedule them, but for these processes to run, they need some resources. Okay, for P1 to run, okay, to do something useful, it needs these two resources. Okay, resource number 1, resource number 2, resource number 3, and resource number 5. If P1 can get these two resources, it can run. So we kind of changed it, and we said that there are 5 philosophers sitting around the round table. Okay, all they do it, they just think and eat. Okay, well, they can think without affecting anybody else, but when they are hungry and they like to eat, this philosopher number 1 needs to get the fork number 1 and fork number 2 and start eating his pasta. Makarnasını çatalla yiyecek. Okay? So otherwise the philosopher number 1 can't eat his food. The same thing is valid for process number or for philosopher number 2. Okay? He thinks, and when he's hungry, he needs to eat. He needs to get these 2 forks, okay, and if he can get 2 of them, then he can eat. Otherwise, he has to wait. He has to wait until P1 is done eating or P3 is done eating. As you see, I mean, there is not much of a, I mean, their standard of hygiene is a little bit different than ours. They are sharing the same fork and etc. Let's ignore that fact. I mean, this is a different culture of philosophy, and let's try to write some code for these 5 processes, and let's see what's happening. And again, why are we talking about this at the end of this processes and threads chapter? Well, there are some inter-process communication issues, and we are going to look at them. This problem is interesting. Okay, so let's write the algorithm for each of these processes or the philosophers. Okay, I have 5 philosophers, and each one is running this function. Of course, I call this function for each process. Okay, I call it with this number 0, 1, 2, 3, 4, right? Process number 0, process number 1, process number 2, and etc. So the process number 0 in an infinite loop, it thinks. To think, it doesn't need anything. It just thinks. It doesn't need any resources. But when he's hungry, he needs to take the fork number 0 and he needs to take the fork number 1, right? So take fork number 0. I'm talking about this P0 now, okay? I is 0. fork number 0 and fork number 1. Modulo n is for P4, right? P4. When I is 4, I plus 1 makes 5. 5 modulo 5 is 0. So the philosopher number 4 is going to take the fork number 4 and fork number 0, right? It's going to be, well, I think I made a mistake. Maybe I shouldn't have done it. Okay, let's get rid of this 5 and 5. This should be P0 and R0. Now it is okay, right? So this P4 needs R4 and R0. P0 needs P0 and R0 and R1. So resources. Okay, so it needs take two forks, and it eats and puts the forks and then thinks again. So obviously there is a race condition. Why there is a race condition? If everybody is running the same algorithm, okay, if everybody is running the same algorithm, this will happen. Suppose all of them are running from P0 to P4, okay. They are thinking that they all got hungry, okay. They all got fork number I. So what does that mean? P0 took fork number 0, P1 took fork number 1, P2 took fork number 2, P3 took fork number 3, and P4 took fork number 4. Okay, so let me maybe show you this way. This one took that way. No, use a different color. Okay, good. This one, and this one, and this one. Okay, and they all took their forks, fork number I. Now each one needs fork I number 1. So P0 needs fork number 1, but it is already taken by P1. It is blocked. P2 took 2, but it needs 3, but it is taken. And it will go that way. And P4 took fork number 4, and it needs 0, but it's taken. So all of them are blocked at this position. Nobody can continue, right? So it's a, what do you call this situation? What? It's a deadlock, right? This is not starvation, right? This is not starvation. Starvation is different. In starvation, some people are using the resources, others can't. In this case, resources are available, okay? Resources are available, but nobody can use it. This is a classical deadlock situation. So this is really a classical deadlock situation. So how do I prevent this? How do I prevent this from happening? Well, I didn't do anything about process synchronization or anything. I have a suggestion for you. How about this? I am going to define a mutex. Okay, mutex I1. Okay, here before I start eating, I will say that down I, and after I am done eating, here I will say up I, right? So I am saying that this is my critical region. Only one process could be in the critical region. When I am hungry, I will take the resources, I will eat. When I am done, I will put the resources, and I am done. Good, right? Did I solve it? Do you see any deadlocks here? Are there any deadlocks? So I solved the deadlock issue, so I am done. Let's go. Are we done? What is the time? What is the time? No, I have 15 more minutes, so I am not done. There is a problem with this. What is this?
Resolve deadlock, but some processes can work simultaneously, but we are only doing one at a time.
Exactly. The problem is this, okay? We are saying that only one philosopher can eat at the same time. In this case, if P1 is eating, Yeah, I know P0 and P2 cannot eat, but I shouldn't prevent P3 or P4 from eating. I mean, P4 can eat at the same time too, right? So this is against the rules of that race condition. Remember our critical region rules? What did the critical region rule? If the resources are available, I should be able to use the resources. Okay? This one, the solution that I gave you, well, it's a solution. At least it prevents the deadlock, doesn't cause any deadlocks. But if I am going to cause these kind of deadlocks, that's not a good thing. You know the classical deadlock picture, gridlock. You have seen those from internet and everything. You know that. Like this is the gridlock traffic. Okay. So the gridlock traffic is this, or maybe I should have picked a real image. These are not good. Yeah, this one is good. Yeah, it's a real image. Make it larger. Can I make it larger? No. Maybe visit. This one is better. Yes. So this is the gridlock, classical gridlock example. As you see, intersection, this traffic try to go that way, cannot go because there is this traffic here, and this traffic cannot go because there is this traffic cannot go because there is this traffic. Resources are available. This space is empty, and the other one is empty, but I cannot use it. So to prevent this deadlock, my solution is kind of like that, okay? Whenever this direction is flowing, prevent everybody from flowing, okay, including this direction too. But I mean, in reality, if this direction is flowing, this direction can flow too, right? Or if this direction is flowing, this direction can flow too. So if I block the traffic, I should block only one of the directions, not three of them, okay? So that's the idea. If you do that kind of a solution, it is going to prevent deadlock, but it's going to be inefficient. Okay? Even though two philosophers can eat at the same time, I am saying that only one philosopher can eat, and that's going to be a problem. So let's solve this problem. How we are going to do that? There is a very nice solution for that, and I'm going to show you the solution, and maybe we will discuss it later. And this is, the philosophers are going to do this. They will think, they will take the forks, and they will eat, and they will put the forks. And the whole number will happen inside this take forks and put forks. Let's look at some data structures. I have n philosophers. There are two macros for left and right. Calculating right is very easy. Just if I am philosopher number I will add a 1 to it and take the modulo n. If I am philosopher number 1, I will add 1, so the modulo n is again 2. So if I am philosopher number 1, my right is 2, my left is 0, right? So for philosopher number 1, right is 2, left is 0. So this is just a simple mathematics. And as a philosopher, I may have 3 states. I might be thinking, I might be eating, or I might be hungry. Remember Patterson's solutions about the alternating processes? They were like, I am interested, or I am inside the critical region. So this is kind of hungry means that I am interested in taking the forks and eating. Okay, so I am thinking, I am eating, or I am interested in getting inside the critical region. And then I have a mutual exclusive semaphore, a mutex, a binary semaphore. Okay, binary semaphore, and I have this is going to be just 0 and 1. And this is another semaphore. It's a semaphore array, and I will keep a semaphore for each philosopher, and initially this will be all 0. Okay, so initially these will be all zero. So if I try to down one of these semaphores, I will be blocked initially. If I try to down this mutex at the beginning, I won't be blocked, but nobody can be in the critical region. And this state is an integer array, and I have 5 of them. Each one can be either thinking, hungry, and eating, and initially its value is 0, 0, 0. They are all thinking. Okay? They are all thinking. So the philosopher I, let's say it is 0, thinks, takes forks, take forks, eat, and put forks. That's what it does. The philosopher number 0 and number 1 and number 2 doesn't matter. Okay, I can make large n as large as I can. So let's look at this. Thinking and eating, of course, I know what they are, and they are thinking is doing, process is doing something. I mean, you may think it that way. You may think it that way. I mean, what's a real life example for these processes? I am I am not sure what kind of well, sometimes, like say, I have a database. Okay, I have a database. I have person names. Okay, let's say name 1, name 2, name 3, name 4, name 5, name 6, etc. It goes that way. Okay, let's say the processes need to make modification in these 2 records in my database. So they need to lock both of them, N1 and N2, one of them. The other one needs to lock N2 and N3. This one needs to lock N3 and N4, etc. So if they need to lock those records before they use it, then they can run into this kind of a problem, deadlock problem. Okay, so let's look at this problem again. Let's look at this fork I, take fork I and take fork I plus 1. This is, okay, this is take fork I. Whenever I like to take the fork I need to get the mutex, okay, and up mutex after this. Okay, so I am in the critical region. I didn't see, note that I did not say, okay, down mutex here and no. I didn't say down mutex here and up mutex here. This is not my critical region. This doesn't work because this makes it possible only for one of the philosophers to use the forks. Okay, not good. Take forks. Say that. Okay, I am in the critical region. I am interested in eating, and there is a function called test I, and I am upping this mutex, so I am out of the critical region. And interestingly, it says that down SI. Remember, SI is a semaphore array, and initially it was 0. Okay, whatever this test I did, if it didn't increase my semaphore value, then I will be blocked at this position. Let's look at what test I does. Test I is simple. It says that if I am hungry, well, I am hungry, right? I set it to hungry. If I am hungry, if my left is not eating, if my right is not eating, then that means that the resources are available. I can take the forks and I start eating, and it's smart, right? I am increasing my semaphore value by 1. Okay, it kind of indicates that whoever wants to make it down, decrement it, they can decrement it. If I can't go into this loop, if I can't go into this if statement, what was the reason? One of the reasons could be my left is eating or my right is eating, right? This cannot be the reason why I cannot go into this loop, because I just set it to hungry, right? So if my left is eating, if my right is eating, if any of them is eating, then I cannot set my state to eating, and I cannot increment the semaphore. So in this case, when I call this set I, test I, okay, it will come here and I will be blocked at this line if I couldn't start eating, right? But if the resources are available, then I can start eating, and this one will be down SI, and I won't be blocked at this point. Okay, so that testing is something weird. I mean, why would I write something like this if I set it to hungry? Why am I checking it hungry? Because I am going to use the set test function in put forks. Let's look at, remember this was take forks. Let's look at this put forks. Put forks does that, okay? Let's go into the critical region. If I am inside the critical region, nobody can be in there, right? Says that, okay, if I am done eating, I will set my state to thinking. I am not hungry. I am not eating, okay? And I will call test for the philosopher on my left and on my right 2 times. What does the test do? Test says that if I am hungry, well, see this one, let's say if I am philosopher number 2, I will call it for philosopher number 1, and I will call it for philosopher number 3. So the philosopher number says that if I am hungry, okay, in this case, now test works. If I am hungry, if my left is not eating and if my right is not eating, okay, well, since I call this on 1 and 3, okay, that means that since I am eating, 1 and 3 cannot eat. I know that either left or right will not be eating anymore, okay. If both of them are not eating, I am going to set myself to eating. I can start eating, and I am upping my semaphore so that if I am blocked here, okay, I will be unblocked and I will continue. And up mutex and it works. Okay, so somebody found this smart solution to this dining philosopher's problem, and the book preferred to put this at the end of this chapter. It's a typical actually deadlock solution. And remember what I said about the deadlocks? Deadlock chapter is chapter number 6 or 7 or something. And whoever teaches operating systems, they are so interested in deadlocks, but in reality, Windows, Linux, Android, iOS, whatever operating system you can think of, we just ignore the deadlocks. We don't handle the deadlocks. Handling deadlocks is something tough. Dynamically trying to detect deadlocks and prevent is something tough. If it happens, then okay, we agree whatever happens, okay? We take whatever happens. If the system will crash, then system will crash. If some processes will hang, they will hang. Yeah, that's it. But this solution is very elegant. This solution is classical. That's why instead of putting this example inside in the deadlocks chapter, they put this at the end of this chapter. And in fact, it's an optional material, but I like to show it to you because it's a very nice and elegant solution. Okay, 1960s they think about the algorithms that way. Everything has to be elegant, everything has to be small, compact, efficient, and we understand everything. After 1960s and 70s, everything has changed. Nowadays, everything is dirty. We don't have to understand anything. All matters is the results, the final result. That's why we do deep learning. Okay, deep learning is a dirty way of solving things without understanding, without knowing what is going on, without understanding the algorithms. Okay, so I favor this kind of solutions, but unfortunately times has changed. I work on deep learning, unfortunately. Otherwise I will go hungry. Why are you looking at me like that? Okay, good. I think I will stop the last problem, which is the reader's writer's problem. Okay, you read it yourself. This one is even a more compact, more elegant, better solution to some other classical deadlock problem. But I will skip this one. On Monday, I will start talking about memory. I am done with the CPU. See you on Monday. Evet.
O soruları teyit ettiği metotta
Ha.
Esa'yı
Take
down
Fox.
yaptığımız yer var ya.
Hayır imza atamazsın.
İmza atmıyorum. Ben de aynısını söylüyorum şu an. Biraz aşağıya inersiniz hocam.
İniyorum.
Burada down SI diyoruz ya hocam.
Evet hocam.
Ondan
Önce mesela test ediyoruz ya.
testin içinde up edemezsek.
Biraz daha aşağı inersiniz dediğimiz önce.
Şimdi bu Mutex için tamam mı?
Tamam.
Evet.
Şundan konuşmuyoruz. Şu testin içerisindeki down'dan konuşuyoruz. Yine
Alttan konuşuyoruz. Evet.
Şimdi şey düşünün. Her bir Philosopher'ın bir tane semaforu var. Başta sıfırlar. Tamam mı?
Evet.
Eğer testin içerisine girdiysem ben testin içerisine.
Evet.
Eğer acıktıysam sağım
müsaitse.
solum yemiyorsa o zaman ben yemeye başlayabilirim ve benim semaforumu bir yapıyorum ki bu testi çalıştıran take forks onu down yapabilsin.
Ama mesela
Ama ben diyelim ki buraya
giremezsek
giremedim.
Bu if'e giremezsen o zaman
edemeyiz.
burası block kullanacak değil mi? Burada
Sonra
block
beni kim
kalacak.
açacak?
Ha?
Evet, bizi
Kim
kim
açacak? Put forks yapan benim komşum bak testi left ve right üzerinde çalıştırıyor. Kendi üzerinde değil. Söyledim ya bak bu dedim bu 2, 1 ve 3 üzerinde çalışıyor dedim.
Ben öncesine çok odaklanmışım oraya. Tamam.
Dinlemiyorsunuz ki aklınızda WhatsApp sadece.
Hayır ya. Öncesine takılı kafam.
Ben bir sonraki nesli böyle görüyorum. Aklınızda sosyal medyadan başka bir şey yok. Dedem bana öyle derdi. Aramaya tutturmuşsun arabaya. Öyle bir çizgi film var. Ne anlıyorsun bundan? Bilmiyorum.
Teşekkür ederiz hocam.
Haklıymış adam ya. Bir daha izledim de hiçbir şey yok o çizgi filmde.
Jenerasyon işte.
Ha?
Jenerasyonların şeyi.
Ha ya dedem haklıymış ya.
Evet.
Vallahi.
Haklılığı diyelim.
Çok haklı bir adam. bu.
Hocam bir de
Ulan bunu kaydetmemişiz bile biz ya. Neyse.
OBS'ten izleniyor zaten genelde.
OBS'ten tamam oradan yapan da o yani bazen insanlar oradan da bakıyorlar.
Hocam bir de ödevde videolardan 15. izleyin demiştiniz.
Şeye kadar olanına